Okay, so this figure 9.8 shows an ideal transformer. And of course, we know that we define the side where the source is connected as the primary, and the side where the voltage is induced, the secondary. Okay, so this is the primary side, this is the secondary side. He also shows that we're defining the primary terms, the number of turns of coil on the primary side is N1, and the number of turns of a wire on the secondary is N2. The primary is connected to a sinusoidal source. And again, remember, none of this works unless the voltage is varying. You know, this transformer is not going to do the things that we've been discussing in a DC application. It has to have this varying AC voltage input to it. The magnetizing current is created by the flux, and this flux, which is indicated here, we call that mutual flux here, and we're saying that all of the flux that is produced is completely linked to the secondary. In other words, you know, when we were looking at particulars of this earlier, you know, we were talking about in terms of the leakage flux, but what we're saying is it's completely linked. And let's see, what else did I leave out? I guess that's it. You know, he says that this flux will vary, you know, based on the sinusoidal input that we have. And so according to the equation 9.1, and you know, there's the peak flux value. So according to 9.1, using equation 9.1, we could define things based on that equation for each side of this transformer. We can do that like this. So I went ahead and got ahead of this a little bit and wrote the two equations that allow us to use equation 9.1. And so, you know, 9.1 described an induced voltage from a source connected to a coil. You know, we explored all that. So, you know, this is showing 9.1 in relation to the primary side, and this is showing equation 9.1 in relation to the secondary side. Now, we can reduce these two equations down, you know, because they have these common terms that we can take out of here, like, you know, here, and well, I didn't mean to take the turns ratio out, but you know, this, and this, and we can end up with this relationship here that shows that the induced voltage on the primary side over the induced voltage on the secondary side is equal to the turns on the primary side over the turns on the secondary side. Okay, and so we give that relationship a particular designation, and we call that the turns ratio. Okay, and it's sort of the fundamental relationship that we look at when we're studying transformers. Okay, so you can see, you know, that the direct relationship between the numbers of turns and the voltage, and so, you know, E1 is a primary voltage, E2 is secondary, primary turns, secondary turns, and then this one thing here that we will use very often in our designation of transformers. Okay, and again, this all works, and it works very well because we are assuming that, you know, this flux that's created completely links both sides of this. Okay, and then along with that description, and let's see if we can, let me clean this up just a little bit here, and I want to point out these phasor diagrams that go along with this discussion here with these equations. Okay, notice that all of the voltages, you know, they're in phase, right? And we know that, you know, when we look at a phasor diagram, you know, they're at the same angle, you know, the same phasor angle across there. So secondary voltage E2 and source voltage EG and primary voltage E1, they are all in phase with each other, and that's represented here. And then the other thing that we want to remember is that when we're dealing with inductors, this relationship that the voltage leads the current by 90 degrees. So, you know, this is an induced voltage here, and then here's the magnetizing current, and it lags the voltage by 90 degrees from here, right? And then the flux that's created is in phase with the current that caused the flux to begin with. So all those relationships are shown there. Let's see, what else can we say here? Okay, the final thing that he mentions, and I'll cut this off and then we'll do example 9.3 in a separate video. He says that this is an ideal transformer and the magnetic circuit is infinitely permeable. So no magnetizing current is required to produce the flux. Okay, under no load conditions, the phasor diagram such as the transformer is identical to 9.8b, except that this is very small. Okay, so again, you know, we're saying it's infinitely permeable. This is this ideal model of the transformer, and you know, we'll contrast that with a practical look, and also when we place it under load. But this is our starting point, and this is our foundation for our definition of the transformer.